Today I'll be presenting on integral bridge design in MIDAS Civil. So myself Suman, so I'm a structural engineer here at MIDAS Research and Development Center, India. So let's go ahead. So these are the contents of my presentation. First I'll introduce you to integral bridges. So what are the different types of integral bridges that we as a designers generally deal, and what are the advantages of integral bridges over other conventional bridges for short span lengths, and what are the integral bridge considerations while designing that you need to take care, and some of the considerations which are really important are this: temperature, soil structure interaction, earth pressure. And then we'll later on at the live demonstration we'll also see how moving load analysis as per South African TMH 7 code can be run in MIDAS Civil. So I'll be giving a live demonstration after the presentation, and then at the end we can have the question and answer session. So I'll be muting your mic, so you can, if you have any questions in between, you just type in the questions box. I'll try to answer them then and there, or if not, I'll answer it at the end of the session. All right. So integral bridge. So you can see a beautiful picture here. So this is a integral bridge, two-span integral bridge. So generally integral bridge are having the abutments, as well as you can have intermediate piers or supports. So integral bridges are basically jointless bridges without any expansion joints within the bridge deck. So you can see a schematic here. So you have a integral abutments and the deck is jointless. So you have a monolithic deck, and it can have a multi-span bridge where you have two piers which can be sitting on the shallow foundation, and there is a possibility that you can have flexible piles as well below the abutment. So unlike conventional abutment bridges where joints are allowed in the bridge to expand and contract to take care about the thermal expansion and contractions, in integral bridges, as we don't have the expansion joints, all this thermal expansion and contractions should be accommodated by the movement of the substructure, which is your abutments and the piles below. Coming to the types of integral bridge, first you have the frame abutments, flexible support abutments, and semi-integral abutments. So these types are differentiated based on the substructure part. First one, where you have the frame abutments, which are called as bank pad abutments. So you can see these two figures, this well as well. So you have the abutment and you have like a bank pad abutments, or you can have the piles below that abutment. So this would be integral. Or you can also have the sleeved piles. So sleeved piles would act as a flexible support which allows the movement in the piles. Or you can have the flexible support abutment in front of the reinforced earth retaining wall in this fashion. And you also have semi-integral abutments. You can see in this figure, this is half integral abutment. So what are the big advantages of integral bridges over conventional bridge? So the major advantages are listed out here. So starting from, it is very easy to construct integral bridges. It's easy and simple construction process, and you have less construction details. You have tremendous reduction in maintenance cost. So this is by far the major advantage. You eliminate the bearings and the expansion joints. So that reduces the life cycle cost of the bridge and the long-term maintenance costs. You have superior ride quality due to deck being continuous. So the rider feels great about the bridge, crossing the bridge. And you have a outstanding seismic performance, and you have no water leakage. So this is also one of the main criteria where you will avoid all the corrosion and all those maintenance things would be avoided, because the water leakage would not happen when the deck is jointless. And it's very easy to do future strengthening as well for this existing bridges. So I have listed shown you some pictures here in this slide. So these are some of the problems, durability problems in conventional bridges. So you need to replace the bearings, you need to go to that location where the bearing sits and you need to replace this bearings periodically, and there, due to the joints, there can be a water leakage or any fluid leakage which can cause corrosions. So these are the main durability problems which are avoided in integral bridges. So increase the durability and the maintenance. Right, let's focus on integral bridge considerations. So while you are doing the integral bridge modeling, what you need to take care. First is your thermal effects. So significant forces can develop in the bridge structure because your deck is continuous and monolithic to the substructure, abutments, piles and soil surrounding the bridge structure. So this magnitude of these forces and the response of the structure is strongly dependent on the stiffness of the bridge structure and the foundation. So because of thermal effects, there is a whole behavior that gets changed because of the deck being jointless and the substructure being monolithic. And if the piles and the soil surrounding the abutments are too stiff, large unwanted forces may develop in the bridge. So you need to take care of this in the design. On the other hand, if the backfill is relatively flexible, the abutment and the foundation soil is stiff, so there would be a difference. So that causes an unwanted yielding of the piles at the bottom of the abutment. Clear? And the integral abutment is a whole together a complex soil structure interaction problem that must be carefully analyzed and designed for optimal performance. Not adequately considering the soil structure interaction, the abutments can reduce bridge service life and result in pile failure. So you need to consider this, including the soil, as a whole problem. So not only focused on the structure, you also need to model the soil around this bridge. First consideration is this temperature effect. So in MIDAS Civil, so you have two options. One is your temperature gradient, which you can apply, and if you have the girders having different depth and you have the nonlinear temperature variation along the girder cross section, which is your temperature gradient load, that can be applied through this command called beam section temperature. So we'll be seeing this in the live demonstration. So you can see this thing is taken from TMS7, this screenshot. So it's mentioned for concrete slab and concrete deck or the box girders. So this is my variation of the temperature that I need to consider. Yeah, this is the important part, which is the soil structure interaction. So the prime concern in integral bridges is this effect of temperature variation on the deformation of the bridge deck. So this thermal expansion and contraction of the bridge deck will affect the back soil, which is adjacent to the abutments, right? So this backfill compaction due to the deck expansion, and there can be a soil slide due to the deck contraction. So this gets repeated as your temperature changes daily or seasonally. Due to this repeated backfill compaction and soil slide, the modulus of subgrade reaction and the pressure distribution of the backfill will vary with the depth. So there is no constant modulus of subgrade reaction for this soil, right? So to model this and to take care about this soil behavior, generally we have two approaches. One is your advanced geotechnical analysis, where you can model the actual soil surrounding the abutments and the foundation, something like this in a particular finite element soil program like our MIDAS GTS, which is a geotechnical software. Or you can go for the second method, which is your practical method, where you are idealizing this soil with the springs, which can be done in MIDAS Civil. So as a structural engineer, we are more probably inclined towards the second approach, as this saves a lot of time. So as I told you, a cycle is the period for the deck expansion to the deck contraction. So how to idealize this soil to springs? So a lot of research has been done, and this pioneer researcher BM Lehen and he has proposed the formulations for the soil springs. So as these cycles are repeated infinitely, the modulus of subgrade reaction of the backfill becomes constant. So these formulations have been used in MIDAS Civil as well. So we'll later see. So assumption of nonlinear behavior of abutment soil springs. So Lehen's assumptions are taken to simulate this nonlinear abutment soil springs. So this is how the program will compute the stiffness of the compression only springs for abutment backfill. So you're modeling the abutment backfill with compression only springs. So if you model with springs and actual response, there is very less difference. So you can actually go for the second one by using the soil springs. So the formulations are detailed out here. So the lateral stress displacement relationship for abutment backfill of integral bridge is this. So this response you need to predict. So for that, you know that we are using Lehen's formulations, where this is the formula for Ks average. So this Ks average depends on a lot of soil parameters. So the program asks for this soil parameters like the void ratio, or the specific gravity, or the cycle factor, density of water, the deck length, abutment height. All these parameters you feed in, the program will calculate this average stiffness, and then it will multiply with the unit area to get the spring stiffness, the equivalent area, and then you'll get the soil spring stiffness. So that's what it's given here. So the abutment springs can be applied automatically. So by that theory, you can actually do the spring stiffness, calculate it manually, but the program allows you to automatically calculate by itself by using this command, which is your integral bridge spring supports. I'll show you this in the program. So everything is automated in MIDAS Civil. This saves a lot of time for you as a designers. You just need to go ahead and click these buttons and give the soil information here, and the program will generate these springs. So the blue ones are your abutment springs, and at the bottom of the abutment, if you're having a footing, then you can go for strip footing spring. If not, if you have piles, then you can give the piles. So the program models this lateral soil with the compression only springs. Coming to the strip footing and the pile springs. So if you have below piles, means the foundation also has piles, then the program will switch to this models, where the strip footing would be a linear spring and the lateral pile spring would be based on this spring model, Ricci and Matlock nonlinear spring model, where the program will create the multilinear springs. So that load versus deflection, which is PY curves of the lateral springs, is given. You can refer this. All these things, all these calculations are given in our MIDAS help manual as well. So the tangential pile spring, which are your skin friction piles, skin friction properties are replicated by this linear spring. So these are the formulations for the calculation of pile springs. So you can refer the literature to know what are all these things. So I'll skip this step. So the program uses all these formulations to calculate the pile spring stiffness, and it provides in this fashion. So you have piles. So you have this pile springs, which are your lateral springs. So lateral soil is modeled with this red springs, and you have the skin friction that you also need to take care. So that skin friction would be modeled with this linear springs, and at the bottom you might be having an end bearing pile. So that time it will also create this end bearing spring. So you need to feed in this data based on the soil tab, whether it is sand, soft clay. So the parameters change. So all the subgrade reaction, earth pressure coefficient, pile diameter, all these parameters you give, the program will calculate the stiffness automatically. And the next consideration is this earth pressure. So this earth pressure changes, you need to consider the appropriate horizontal soil pressure coefficient. Can be K0 active, or it can be passive. So the program has this command hydrostatic pressure load where you can give the gradient accordingly. The program applies this. So this is also one of the very good feature. So I'll show in the demonstration. So let's quickly jump into the program. So I've opened MIDAS Civil. So this is the starting page of MIDAS Civil. I'll press new. Just a 1-minute introduction of MIDAS Civil as a program. Left side you have tree menu. This is the model window. You have command message and the analysis message. And these are the main tabs starting from view till the tools. All the options are there here. You have file icon, import, export options. And this is tree menu 2. You can right click here and select this tree menu 2. Alright. So as you all know, we have dedicated wizards here in the structure tab. So let's use this RC frame box culvert wizard. I'll click this. So this opens up the wizard. So you have longitudinal transfers and loads, information that you need to feed in. First is the material. Let me create the material. I'll add a concrete material like M40. Click OK. Select that material. So let's take a span length of 20 meters. So you can see in this bitmap image. So this is your span 1. So this is 20 meters I'll take. I'll take the wing wall thickness as 0.5. Plate size 1 meter. Skew angle, right now I won't give any skew for the slab for this bridge. If you have radius, you can give in. And these are all the dimensions. By seeing this figure, you need to enter. T1 is the top slab thickness, and T2 is this intermediate support. T3 is your abutment thickness. So all this information, to save time, I have created a template of it. So let me open the template where all the values are there. Click open. So I have taken T1 as 0.2, T3 as 1.2 meter. So the thickness of abutment is 1.2 meter. And I'll take the wing wall, this dimension as 6 meter. All these dimensions as there. And let's go to the transfers. So I've selected this type of transfers, and I'll give this B3 as 0.5. All these dimensions from this image. I'll go to loads. I'll select the sulfate, pavement, and the soil, and this weight densities I'll give. So these are all the loads. You just need to give the weight densities by the dimensions that you have given in these two tabs. The program will apply the corresponding loads. So I have given the system temperature as plus 20 degrees, plus or minus, and temperature gradient as delta T as 5, shrinkage strain. I'll click OK. So you see, within no time our integral bridge is created. So this is our slab, which is your 0.2. So below it you'll be having the girders. So the program has created all these things for you. You have the supports, the bottom supports, learn display, and then you have this thicknesses based on the dimension that we have given. The material M40, click escape, and you have this dead loads. First the dead loads based on the transfers information. It has provided the dead load, the temperature gradient load for the slab, system temperature, and then the earth pressure. Even for the wing walls it's applied, and the shrinkage load. Alright, so let's start the modeling of the girders, just to show you how you can model quickly the girders. So you can go to node and element, create elements. So here I wanted to add a girder section, so I'll just take one girder, of solid rectangle. Give the height as 1 and the width as 0.5. Give some name. Give the offset as center top. Okay. All right. So let's go to works. So to select the deck, so you can directly click on this deck thickness. Only those elements would be selected and this is activated. Now you can easily create your girders. So I'm just randomly creating some girders here. 1 here as well, 2, then I'll skip 1 and this is 3, this 4th girder. Alright, so this is my girder. I'll activate all. Let me create a diaphragm as well. So I can double click here. So these are my girders. In between, let's have a diaphragm. Create elements. I'll take some diaphragm. Just copy this. Give this as diaphragm. I'll give the width as 0.3. This as 0.8. Okay. So let's try to create here this diaphragm. Alright. So this completes our modeling of the superstructure. Now you can go ahead for the analysis. Before that, let's see the soil spring application. So first, let's go to boundary. And here is this integral bridge spring supports that I was talking in the presentation that was highlighted. So this you have soil spring type as abutment spring as well as the pile spring. So let's first give the abutment springs. So we don't have the piles. Let's try to create some random piles here. So I'll try to activate the abutments only. Go to left view. Let's create some piles. So here I'll select this extrude command. This is also one of the fantastic feature where you can extrude from node to line or line to planar or planar to solid. Quickly you can generate the elements you wanted. So let me select this nodes. Let's create a section for piles. Just select the solid round. User, give it as 0.6. I'll give the name as piles. Click OK. Select that section. Unequal distance in Z direction. Let's give the pile length as 20 meters in the negative Z direction. Click apply. So these are our piles. Activate all. Now let's go to this properties and boundaries and then create the boundary conditions. Abutment springs. So here you can see the figure. So let's activate the abutments. So this is your normal face. So in the direction it is plus normal. So let's see our local direction of this place. So you can go to element and click on local axis. Go to top view. So this Z is outward and this Z is outward. So we can select all the elements of the abutments. So the element list comes up here. So if you have any strip footing at the bottom, so you can select that node list. So right now we have piles. I'm not giving any strip footing. So the abutment height, let's select the abutment height. Abutment width is 1.2 and the deck length I've given it as 20. The void ratio randomly I'll select 0.8. Specific gravity of the soils, the cycle factor, so you can give it this as 2, and this thermal expansion for the abutment, it's in the Fahrenheit units. Let's change the units. Select Celsius. So let's give some 20 delta T, and alpha would be 1 e power minus 5. I'm not giving the strip footing data. Just click apply. Let me save this. Right, so this applies the abutment springs. You can see here, these are compression only springs. You can go to properties. These are compression only springs, so the soil generally takes only the compression, so it's modeled with compression only spring, and the stiffness has been auto calculated by the program. So this spring stiffness is in this direction, which is your global direction, which is in your X, and these are all the springs. So you can go to tables, and if you want to give any of them manually, you can change this. First create in this fashion, and then you can change the stiffnesses as per your need. If your soil is multi-layered and you wanted to change the stiffness, so while you are creating the integral bridge here, so for some length, if you have this soil parameters, you can give that, and those springs would be generated. And if you want to change the below soil spring parameters, you can change them and then create the nonlinear spring supports accordingly for multi-layered soil. So let's create the pile springs now. I'll just click this reset. Yes, here I'll select the pile springs. So here you'll have this 2 springs, which are your lateral spring as well as the skin friction spring. I'll select the soil type as sand. So if you select soft clay or stiff clay, the parameters will change. I'll select sand. The ground level, I'll select the top, which is at 0, or I'll just give it as origin. Just type in 0. The pile diameter is 0.6 meter. Unit weight of soil around the piles is 20, I'll assume, and this I'll take it as 0.5. The modulus of subgrade reaction, I'll select 20,000 for the soil here, and the frictional angle 35 suppose, and the initial soil modulus, so I'll select medium soil, so the stiffness is this. Now I'll select the piles, I'll click apply. So that simple is the definition of these springs. So if you go for manual definition, it will take a lot of time for you. This has been automated, fully automated in the program. So these are all the boundary conditions. Just show you what are all the boundary conditions again. So these are your linear springs, right? So this is for skin friction, and these are your abutment lateral springs, and these are your multilinear springs, which are for the piles. So these are the lateral spring supports for the piles, which are multilinear as per the Rees model. So you can have this multilinear spring here. So these are all the stiffnesses and the PY curves that the program has created automatically. So this is the soil structure interaction that can be performed in MIDAS Civil. So now the supports are defined, and the loading. Coming to the loading, the program has generated this loadings as we have generated the model from the wizard. But if you want to apply the temperature loads, you need to go to load, click on temperature pre-stress, and here you have temperature loads. So you have these options: element temperature, temperature gradient, beam section temperature. Let me explain this in detail. This element temperature is for the beam elements or any elements. Like if you have temperature gradient, you can give this, and if you, this is a uniform expansion and contraction loading. These two are for the temperature gradient, which is in the cross section. Suppose the beam section temperature, you can give this. and system temperature is the expansion and contraction, which is nothing but increase in temperature and decrease in temperature for the entire model. So that can be given for the system temperature, whereas this is only for the elements. So that's the difference. So the program has given this, so it's very straightforward. Let's run the model. I'll go to results. Let's see the deformations first. Click displacement contour. This is for the self weight. Select the deform, click apply. So this is the deformation pattern. Let's see the temperature positive gradient deformation. So this is highly exaggerated one. You can see the units. So let's select this mm. It's only 0.5 mm due to this temperature gradient load. Let's see for the system temperature. So there is an increase of temperature. All this deck and the girders started expanding, and you have the negative temperature. So you can see here there's a negative temperature. So let's see the reactions for this system temperature positive, because all the soil which is there here at the backside behind the abutment should give you the reactions and the resistance. So let's see whether in this case we have the resistance. Yes. So you can turn on the values. You can see the reactions of the abutment springs. So this is the interaction that I was talking about. So you need to design your abutments, and all this temperature loading is being taken care by the flexibility of the abutments and the piles here. So this deformation should be accommodated by the substructure. So let me open a fairly complex model now, as this is a simple model which also has the soil structure interaction. So this is partially completed model. Just wanted to show you some other commands. So in this model, so you have this sections, some girder section of this type, and then I have this dummy cross beams and the cross girders of this cross section. So these are your sections. Materials M40 I'll take. The thickness. So for this, this is modeled with the plates, and the pier cap is modeled with the plates. So I can set this to meters. Okay, and then you have this supports. So let's delete this as well. And then you have these supports which are defined here at the bottom. Then you have this elastic links which is connecting the superstructure to the substructure here. Here we'll be modeling the abutments now. So these are all the loads that is being applied, and TMH7 is used for the moving load analysis. So for now, let's start modeling the abutments. I'll just show you some tricks how you can quickly model the abutments for this type of curved bridge as well. So I'll go to node and element, click on extrude. So here we'll try to use this line to planar. So you can create the dummy line first here. So let's and then extrude the abutment. I'll go to create elements. Just select this cross girder type, and let's create the elements here. Now let's go to extrude option. Select line to planar. Now I'll delete the source from where I'm extruding. I'll select this line elements, and from here I wanted to extrude it downwards, so I'll select 1 meter is the thickness of my abutment, and you have this finite element thick or thin plate you can use for abutment modeling. In the Z direction, I'll take it as 10 meters, the abutment length in the negative Z. Click apply. So the abutment is modeled. Then you can go to works, select the abutments and activate that. We need to check the local axis. So you can see Z is in this direction and this should be the outward direction. So let's try to reverse it. I'll go to node and element, click change parameters, click on reverse element local axis, planar, just select this abutment, click apply. Let's reset this. Now let's start extruding the piles. So I'll click on extrude, node and line element. I'll select this bottom nodes, then select the piles and unequal distance Z direction. So I'll just extrude this in 20 meters -1. Click apply. So I have modeled the piles and the abutments. So you can appreciate how quickly you can model the substructure through these commands. Now let's give the boundary conditions, the integral bridge, spring supports. First let's give the abutment supports. Select the abutments, activate. So the element list, select all. So all the element lists will come up automatically. I don't want to give the footing because I have the piles. Abutment height, I can directly click here and then drag. So this is 10 meters. So the width is 1 meter. So what is the deck length of this curved bridge? You need to have the curved deck length. So I already have that. It's 152.94 is the whole bridge length. Void ratio, I'll just take 0.5, 2.652 plus 20 and minus 20. Select M40 for your alpha. Just hit apply. So the program now creates this compression only springs and display. I'll just activate all, click this initial view. Let's go to pile springs and create the pile springs for this. Just select the stiff clay, or I'll just select the sand for now. So my ground level is at origin. Just give this as 0. Pile diameter, what is the pile diameter? So it's 1 meter. Give it as 1 meter. 20.5 and this I'll give it as 18,000 subgrade modulus. Then select the piles, click apply. So this completes the boundary conditions for this model. Let's go to initial view. Now let's see the temperature application, the loading application for the girders. So right now you have this beam temperature load. I'll just delete this and show you how you can quickly apply the temperature load. Go to beam section temperature. Right now I've deleted the temperature gradient positive. I'll reapply that. So as you know, we need to apply this nonlinear temperature gradient across the girder. So I'll just select this end top as reference. So at the top, the temperature is, so let's go to PSC here, the section type PSC or composite. So where the B would be automatically calculated. So I'll select the width to be section. The program will calculate the B automatically. At the top, what is the temperature? It's 13.5. Sorry, this is 13.5, and this is at 0th level. And then suppose I'll take it as 0.8 meter below. I'll give it as 3.5. I'll add. Now from 0.8, it is 3.5 to 0. Something like 1 meter. Click add. As a total girder depth is 1.6, I'll just give this as 1.4, give the T1 as 0 and this as 1.6. At the bottom of the girder, I'll give a temperature of 2.5 suppose. Click add. So for positive, you need to give all the plus, and for negative temperature gradient, just need to give minus 2.5. Negative sign need to be included. So I'll select the girders. So these are my girders. Select this, click apply. So you can select any one element and see, just activate. So this is the temperature gradient variation. So from here till here, so the top temperature is 13.5, here it is 3.5, and then it gets to 0. At the bottom it's 2.5, and here it's 0. So this temperature, cross-section temperature variation will create a lot of effect on the integral bridge. So let's see that. Wait all, just click on this initial view. And for system temperature, you just need to directly give this minus 20 or plus 45. For rise and fall I have given plus, for rise I have given plus 45 delta T, and temperature fall delta T is minus 20. Now let's see the application of TMH7 moving load code onto this curved bridge. So let me show you some slides. So in MIDAS Civil, TMH7 code is implemented. It's full-fledged TMH7 moving load code. So NA vehicle would be considered in this fashion. So you have this formulation given in the code. The same have been replicated in the program. So you need to consider the longitudinal distribution, transverse distribution, all these considerations. Next is your NB vehicle. So all this X distance have been taken care. So the program will change these distances to create the max and min effects. Similarly, NC vehicle, you have the variation in the pressure loads. So the program will automatically consider them. And if you have any permit truck, you can also run these permit trucks on your bridge. So all lanes NA loaded would look like this. Single lane NB load. So the program will place the loads accordingly to create the negative effect as well. And NC load, single lane. And if you have any dual carriage, the program will also consider the 2/3 of NA load. You also have the user defined load case. So moving load optimizer is a special feature in MIDAS Civil, where you have one is your regular optimization, where if you have the lane width which is more than the vehicle width, so the program will keep this vehicle in 3 positions: center, left and right. So left, right and the center, and it will run through your bridge. So this is your regular optimization. We also have a multi-point optimization. You just need to give the full deck width as an optimization lane and some details of the vehicle, like the lane width, what is the margin and what is the wheel spacing. So the program will run the vehicle and optimize in this whole optimization lane width. So it will consider the transverse widths and it will place in every location. Then you also can generate the concurrent member force reactions, something like these are maximum reactions. So these are your concurrent reactions. You can get it in the tabular format. Right, let's go to the program now. So here you have to go to load, moving load, select South Africa, and for NA and NB, if you are trying to create through line lanes, you need to define many number of lanes, like the 2 lanes. So the width of this bridge is 7.5. So you can query nodes, something around 7.35 is the width. So you can have 2 lanes defined, or you can select moving load optimization. So line lanes should be used when you have the grillage superstructure. If you have a plate superstructure, like the deck has a plate, then you can go for this traffic surface lanes or the moving load optimization for surface lanes. So right now these are grillage beam elements. So I'll go for this traffic line lanes. I'll right click uh, this traffic line lane optimization for NA and NB. NA and NB, and the optimization lane width, I'll give it as 7 meters. The lane width is 7 by 2. Like you're having 2 lanes, so it's 3.5 meters, and you need to select this cross beams. So this cross beams are nothing but this cross girder group. So you just need to group all these elements for the transfer distribution. You need to select that group here, and then you can pick the girder reference line and give the lane. So let me display that. So this is the lane that I have defined from the reference line, and this lane is not at the center. It will switch. The program will optimize throughout this 7-meter optimization lane width. Coming to this one, NA and NB, so this would be optimized. And coming to NC vehicle, so it should be running in the center line as per the code. So that's why I've given a traffic line lane. Click properties as this. So I have selected the traffic lane optimization and I have ran through its center. You can see it here. All right. So this completes the lane definitions. I'll go to vehicles and then you can add standard and select NA, NB and NC, the required vehicles. Then you can go to the moving load cases and start defining this moving load cases. For NA, as I am optimizing, so I'll select moving load optimization, give this information. The number of loaded lanes, I'll select 2. For NB as well, I'll select the moving load optimization. But for NC, I have given it a separate traffic line lane here. So I'll select NC type and select that lane. So this is a 3-step process. First you define the line lanes, and then you define the vehicles, and then the moving load cases, how the vehicle should move on your bridge. Alright, so let's run the model. To save time, I have already ran this model. Let me open that. Just open that model and let's see the results. Just a minute. Alright, the analysis results have not been completed yet. So let's run it and check. Alright, this would take a bit of time for the moving load optimization. What I'll do is I'll just delete this moving load and then run this static load. So if you have any questions, you can type it in the questions box. Alright, you can go to results, go to deformations, select the temperature rise, fall, click apply. So this is the deformations. And you can go to bending moment diagram. So these are your bending moment diagrams. So you can go to stress, beam stresses diagram and check the stresses in the beams. Similarly, you can check the reactions. So you can go to results table, reactions, select temperature rise, click OK. So these are all the reactions which are Excel friendly. You can copy paste back in the Excel file. And then you can make the load combinations here and then check the results. So there are some questions here now. Just a moment. So the question is, what is the difference between two subgrade modulus in the pile box? So I'll go to boundary, unlock this. So there is only one subgrade reaction that you need to enter, and if you change the soil type, it will change. Alright, so you only have one subgrade reaction. So does the MIDAS account for secondary effects due to continuous structure? Yes, the program will account for the secondary effects. So if you have any continuous span like this, so whatever the secondary effects are there, it will account for it. So what is the function or the purpose of the dummy cross beams? What stiffness is assigned to them? So this is a question from Mr. Andrew. So this dummy cross beams are required to transversely distribute the traffic load. So you can refer our help manual where the figures are given. So what happens is the load should be transferred to the deck and from deck to the girders. So for this you need to have this cross beams in the moving load definition. So the program will consider the distribution between the girders, because not a single, if a vehicle comes, the entire vehicle load shouldn't go to a lane or only a single girder. Should go and distribute to the different girders. So this cross beams will help in the distribution. So there is one question from France. Is the width not the length of the abutment wall? So in the integral bridge, yes, this should be the width in this direction. So it shouldn't be the thickness, it should be the width. Yes, I thought this is one, yeah. This should be the width. So you need to click this button and select this width. All right. So there is a question from France as well, like why is the foundation linked to the same void ratio and FCYC as the backfill? So these materials normally differ. So that's how the formulations are. So for the abutment, for the backfill, so we only have one void ratio that's considered in the Lehen's formulation. So you can refer it, and if you have any issues with that, so you can write to us. I think this void ratio slide that I've shown you includes only one void ratio. So if you are talking about multi-layered soil where the void ratios and those things are changing, then that time you need to change the springs. All right, if you have any other questions, just type it in the questions box. Is FCYC constant? Yes. So let me show you that slide. So FCYC is your cycle factor. So if you want to change, you have full freedom, right? So if you want to change it, you can change this cycle factor. So next question is from Iqbal. How would you input seismic loading? See, for seismic loading, are you talking about the static loads? So you can go to your element loads or the pressure loads and apply the static loading to your substructure, or you have this dynamic analysis like the response spectrum analysis that you can do for the bridge. So there's a question from Mr. David. TMH 7 part 1 and 2 requires a consideration of horizontal loads from skidding and braking in combination with respect to different traffic. Yes, I do agree with you. So you need to apply this manually, the centrifugal and the horizontal braking and traction forces from the static loads. Create your load cases and apply through these commands. Go to boundary, click on integral bridge. So here this is pile springs. Understand. So you are Mr. France is asking that there are two subgrade reactions. So this is the one which is the coefficient of subgrade reaction for the soil that you determined from geotechnical testing. And this is the initial soil modulus. So this depends on the soil type, whether it's loose, medium or sand. So are the lateral springs non-linear? Yes, they are non-linear. So non-linear in the sense this compression only springs are considered as non-linear, and you have this multilinear springs for the piles. So this initial modulus is used in the calculations for the pile spring as per the Rees MATLAB model. So in this formulations, so you need to have the coefficient, this initial modulus in the calculations. Alright, if you have any questions, you can type in the questions box. So I'll spend some 5 minutes answering them. Okay, I just realized that we have crossed the 1 hour mark. So let me conclude the presentation. This is MIDAS Civil Lite version where you get all these features like the integral bridge wizard soil structure is available in the MIDAS Civil Lite version. So you can also do the settlement analysis and you can also do the construction stay analysis here. So there is a question from Mr. David. And the reinforced frame analysis window, we are required to input surcharge and temperature gradient and system. I assume we will have to set them 0 and only input them in the load window. Yes. If you have varied loads, you need to give it as manual. If you have the girders and this one. So what I've shown you is the quick generation from the wizard, and then you can later on change as per your project. So I also wanted to show you this one interesting model. This is a steel composite integral bridge. So there are some construction stages which are defined. So this is your substructure construction. The girders come up and the bracings. and then the deck is poured and it becomes composite with the integral, then you can do the post CS analysis and run the movie rules. Right? You can then do the construction stay analysis for this type of incremental bridges as well. Alright, so these are our MIDAS Civil users in South Africa. So all these companies are using day in, day out our program. So thank you all for your patience. I hope you have enjoyed the presentation. So if you have any questions regarding the software and its purchases, so you can go and email to this email address ashish@midascivil.com. And if you have any technical questions, you can go visit our www.globalsupport.midasusers.com.